Right, so now we're going to look at discrete probability distributions. Okay, so for any random variable, there are corresponding probability distribution, which describes the probability of a variable happening. Okay, so taking a particular value. So this is the bit that can confuse. If x is the random variable, it can have possible values x1, x2, x3, x4, and so on. Okay, and each of those has a probability assigned to it. And then we have the distribution function is described like this: p of x equals pi, I equals a bunch of values, which sounds like something very hard to understand. So what we're going to do is we'll just go through the formal maths of it, and then we'll look at some actual examples so it become clear. Now this means the probability has to be between 0 and 1. It's impossible to have a probability less than 0, and it's possible to have a probability bigger than 1. Okay, so each probability, no matter which one you have, from 1 to n, all the different probabilities must be between 0 and 1. And this means all the probabilities of your distribution must add up to 1. Okay, so all the different outcomes you can have must have a probability that totals up to 1. And that is quite a key one for some of the problems we're going to solve. Okay, and basically, if you have a set of probabilities, that would describe the probability distribution of x. So in this example, we've got x is the number of heads being obtained when 2 coins are tossed. So you can either have no heads, 1 head, or 2 head. Okay, and we get 0 heads. Well, that's tail, tail, and that can happen one way. We can have 1 head happen 2 ways, so tail, head, head, tail, and we can have 2 heads happen 1 way. So there's 4 possible outcomes equally likely. So we can see the probability of getting no heads, which is 2 tails, is 1/4. The probability of getting 1 head, there's 2 ways of doing that, each of them 1/4. So that gives you a half for getting the probability of 1 head. And then 2 heads, the probability of getting that is 1/4. So these are all the different PIs it's talking about. So, and we can see all the probabilities are between 0 and 1. And if we add up all the probabilities, they add up all to 1. So we've got all these 3 conditions satisfied. You can show your probabilities in many different ways. You can do a table of all the values. The little x indicates the individual values that the big X can take. And probability of big X equaling little x, the variable equaling one of these values, is given by these probabilities. We can graph them as bars, or we can graph them as lines. Now, a uniform discrete random variable is one where the probability is all the same. So if we had all the probabilities equal to 1/3, that would be a uniform distribution. Okay, so that, and a dice is a good example of a uniform discrete random variable. So the score on each dice all has a probability of 1/6 occurring. So therefore, it's always the same probability. Therefore, it's a uniform discrete random variable. How do you find the mode and the median? Well, the mode is the one with the highest probability. We're going back to this situation here. This has the highest probability, so the mode is 1. Okay. How do you find the median? Well, the median is where the probability of being less than or equal to that value is 0.5. Now we can see the probability of being less than or equal to 1. Okay. Well, not less than or equal to 1 in this case, because it's 0.75. It's where the probability that you're equal 0.5 or less gives you your median value. So half the probability happens that way, half the probability is this way. So therefore, the median in this value is going to be 1. Let's look at some proper examples. So state whether each of the following is a valid probability distribution. So I'll just let you think about each one in turn for a few seconds before I go on to do it and explain what we're going to look for to check that it is a valid probability distribution. So let's look at the first one. We've got, in part 1, we've got 0.2. We add these all up. We can see 0.2 plus 0.4 is 0.6, plus 0.25 will get me to 0.85, plus another 0.15, that will get me to 1. So the probabilities all add up to 1. every single probability is between 0 and 1, so therefore it's a valid probability distribution. This one, we can see the probabilities add up to 0.5, 0.9, 1.1. So because the probabilities all add up to a number bigger than 1, this is not a valid probability distribution. Here, 0.2, 0.2, 0.2, 0.2, we've got a good example of a uniform discrete probability distribution. All the probabilities are the same, okay? They add up to 1, so this one is okay. And this one we can see straight away without even thinking it's not okay, because we have a probability that's not bigger than 1, okay? And it's not less than or equal. It's got to be between 0 and 1, okay? And this is a negative, so it can't be that. For which distributions A is a uniform random variable, well, we just saw that it was part 3, because all the probabilities were exactly the same. Right, here's a bit of problem solving to go in our question. Find k in each of these probability distributions. Well, we know that 0.3 plus k plus 0.5 must equal 1. So therefore, k will equal 0.2. In this one, we got k plus 2k plus 3k plus k equals 1. So that's 4k, 6k, 7k equals 1. So k is equal to 1/7. So we're using the fact that probabilities add up to 1 to find k in both these problems. Right, we're going to consider the probability distribution alongside here. Okay, and we want to start off by finding the value of a. So we know these probabilities must add up to 1. So for part A, we got 0.1 plus 0.25 plus 0.45 plus a equals 1. So we've got 0.35, that's going to be 0.8 plus a equals 1. So a will equal 0.2. Is it a uniform discrete random variable? No, because the probabilities are not the same. They're not the same throughout, so therefore it's not a uniform discrete random variable. State the mode of the distribution is the one with the highest probability. So the mode, part C, is equal to 2. Find the probability that x is greater than or equal to 2. So therefore greater than or equal to 2 will include 2 and include 3. So it's going to be equal to 0.45 plus 0.2. So it's going to be equal to 0.65. Right. Show the following are valid probability mass functions. Now, we've not looked at probability mass functions. A probability mass function is where the probability is given by a function for particular values of x. So let's do a little table for this. So these are our values of x, 1, 2, and 3. And we want to find the probability that x equals x. And we use this function to find it. So the function is x plus 1 divided by 10. So x is 0 plus 1 divided by 10 gives me 10. Same again. 1 plus 1 is 2 divided by 10 is 2 tenths. 2 plus 1 is 3 tenths. 3 plus 1 is 4 tenths. And if we add them all up, so we get 1 tenth plus 2 tenths plus 3 tenths plus 4 tenths, we get equals to 1. Therefore valid probability mass function. Part B, let's do the same again. X 0, 1, 2, 3. Oh no, we don't have 0 this time. Let's just rub that out because it only has 1, 2, and 3 as our values. So probability that x equals x. So 6, when x is 1, the probability that our random variable will equal 1 is 6 over 11. When it equals 2, it will be 6 over 22. When it equals 3, it will be 6 over 33. So we need to add those up. And because we got to show that we probably ought to put the same denominator. So we're into 66, so we're going to times this by 6, so that'll give me 36. Times this one by 3, that'll give me 18. Times this one by 2, that will give me 12. And we add these all up, we get 66 over 66, which is equal to 1. Therefore, it's a valid PMF, because all the properties are between 0 to 1, and all the properties add up to 1.